What's up, mathematicians? This video is an introduction to radians, and let's dive right in. So, most likely you are familiar with the angle measurement, which we call degrees. Okay, and just to make sure we're all on the same page here, the degrees measurement divides the full circle up into 360 slices. So if you're measuring in degrees, then to go all the way around the circle, is a total of 360 degrees. Okay. And these are all individual, very narrow little slices. So one question we could ask is, why 360 degrees? Why not 100 degrees, like percentages or something else? One explanation is it is possibly because it is close to the number of days in a year. Of days in a year. So if you think about it, as the Earth rotates around the Sun, it covers approximately 1 degree per day in that trip around the Sun. Of course, there are 365 days in a year, so it's not exactly 1 degree per day, but it's pretty close. Another reason why 360 probably became, what seemed advantageous is 360 has lots and lots of factors. Okay, you can go ahead and try to list all the factors in 360. I'll give the first few. So 2, 3, 4, 5, 6, 7 is actually the first natural number we come to that is not a factor of 360, but then we have 8, 9, 10, just skip 11, we get 12, and then I think we skip to 15, skip 13 and 14. So yeah, so I'm not going to list them all, but suffices to say, my pen is acting up a little bit here. Suffices to say, there are a lot of factors. And so what does it mean? If you want to divide a circle in half, or in thirds, or in fifths, or in ninths, or in tenths, or in 24ths, or what have you, you can divide it evenly using degrees, because all of those numbers divide evenly into 360. So you can easily divide a circle into 10 equal parts using degrees, into 12 equal parts using degrees, etc. Okay, so it's easy to quantify fractions of a circle because of the number of factors it has. But there is a big disadvantage. Disadvantage to degrees. Okay. So what is the big disadvantage to degrees? So it doesn't easily give us information about circular distance. Okay. So when we're dealing with degrees, it makes it easy to divide a circle into equal parts that all have a whole number of degrees, but it doesn't easily give us information or a tool for computation about circular distance. And the fact is, if we want to describe circular motion, we need to find circular distance. Okay, so to describe to describe motion, we need to know distance. Distance is a key piece of information. And this is a course about motion. So we want to be dealing with this idea of distance. So what do we do? All right, so consider we have a circle with radius 1. Okay. Radius 1 unit. And let's go ahead and draw a little circle. So I'm going to go ahead and draw a little XY plane. Alright, so right in here. Alright. And I know my circle's probably not going to be perfect, but I will do my best. Okay, so there's my circle. And since the circle is radius 1, of course the origin is at the point 0, 0. And so, oops. And so this point right here, that's 1, 0. Right here, this is 0, 1. This point over here is -1, 0. And this point down here, 0, -1. And so there we go. That's a circle with radius 1 on the coordinate plane. And the question is, what is the distance around the circle? Around the circle. Well, you may be familiar with some formulas involving, dimensions and such, measurements of circles, and you say, well, okay, first of all, let's write down the radius. The radius is clearly 1. We specified that up here, and also we see from the center to a point on the circle is 1 unit. So, okay, great. So the radius is 1. Okay, well then the circumference is equal to 2 pi, because the formula for circumference is 2 pi r, and r is 1, and so the circumference is 2 pi, which, by the way, is equal to the mathematical constant tau, which is approximately equal to 6.28. So we'll mostly be using pi in this class, but I think it's also worth knowing about the constant tau. Tau is just equal to 2 pi, and some people prefer to use tau, but most textbooks use 2 pi, so we'll stick mostly to, use pi, and in this case 2 pi, so we'll stick mostly to pi. Now, if we think about our degrees, we know that one revolution around a circle is equal to 360 degrees. Okay, but if we think about the distance with the radius being 1, a circle with radius 1, that is also equal to the length 2 pi. And this is where radians comes in. So radians give us the distance around the circle with radius 1. Instead of using degrees, we can use this measurement of distance around the circle. So 2 pi radians. This is sort of our first equation of the day. 360 degrees equals 2 pi radians. Or, for those who prefer it, tau radians. Okay. Okay, so that's a useful piece of information. And hang on one second, I'm realizing that I'm going to have to add some more space to the bottom here. Hang on, I grab my little mouse here. Okay. Oops. Alright, sorry about this. Alright, I'm just trying to create a little more space down here. Nope, doesn't want to do it. Okay, there we go. That should work. Okay, so getting back to our question at hand. So, as I just stated, 360 degrees is equal to 2 pi radians, and I will abbreviate it as RAD. RAD meaning radians. Okay, so let's kind of take this in two directions here. I'll move this up just a little bit. And so, first of all, we can write that as 360 degrees, and I'll abbreviate it DG, is equal to 2 pi radians. And if I divide both sides of this equation by 360, okay, then, well, what happens? This will cancel out with this, and what I'll end up with is that the degrees is equal to 2 pi divided by, oops, sorry about that. I'm going to actually reduce this. So divide top and bottom by 2. So instead of 2 pi over 360, I'm going to write it as pi over 180 degrees, or just 180 radians. Okay. So degrees is equal to pi times the number, sorry, pi times 180, sorry, pi over 180 times the number of radians. And so so what that means is that 1 degree is equal to pi over 180 radians. And for any number of degrees, theta I can put in here. Theta degrees equals theta times pi over 180 radians. So if you want to convert from degrees, let's say you have an angle in degrees, you want to convert it to radians, all you do is you take the angle, you multiply it by pi over 180. Okay? That is how you turn degrees into radians. Okay, what if you want to turn radians into degrees? Well, it's pretty similar, right? So we have 2 pi radians is equal to 360 degrees. Well, now we're going to divide both sides by 2 pi. Okay, so those cancel out, and what that means is that radians is equal to 180 over pi, because I divided 2 from the top and bottom there, degrees. So 1 radian is equal to 180 over pi degrees. And so if I have some angle in degrees, or sorry, some angle in radians, and I will find the degrees, I take the angle times 180 over pi. So in order to convert radians to degrees, my formula is the angle theta times 180 divided by pi. So there we go. We have our little formulas to convert. Okay, and so based on this, let's say we have an angle of 1 radian. Well, we know that 1 radian is equal to 1 times 180 over pi. Okay, and we can go to the calculator here and say, okay, 180 divided by pi, hit enter, and we see that 1 radian is approximately equal to 57.3 degrees. Alright, so I'm not going to draw this perfectly to scale, but just as an illustration, I'm going to draw a little, yeah, I'm trying to draw this pretty straight using my lovely dots, right? Alright, sometimes I do a better job than other times. Okay, so again, this won't be perfect. You can draw, you can use a protractor to get yours really precise, but I'm going to go ahead and say that this right here is, and actually I'm not even going to put that arrow in there. Okay, this angle right here is, and I'm just going to use it like that. Okay, so 57.3 degrees, or 1 radian, which equals 1 radian. And I don't really have space, so I'm just going to erase that. But you can see right up here, 1 radian is equal to 57.3 degrees. Okay, so what that means is that if this right here, like if I take my angle, okay, and I say this length right here is 1 unit, then this length right here, this arc length, is also 1 unit. And that's what it means, you know, to be working with radians. That whatever angle you're talking about is equal to the length of the arc if the circle, or the portion of the circle, has a radius of 1 unit. Okay, so, you know, like, what if we want to be a little bit more general about this? So let's draw another little coordinate axis here. Okay, and we're going to say, okay, this length right here is, or sorry, this angle right here is some angle theta. I'm not going to specify what it is. It could be 57.3 degrees, it could be 20 degrees, it could be any number of degrees. And if this were 1 unit, then the length of this arc right here, maybe I should actually just make that line end right there. Okay, so the length of that arc is equal to theta units. Okay, if theta is in radians. And so let's specify this theta is in, you know, radians. Okay, so what if instead of 1 unit, I decided that this was some radius r units instead of 1 unit? Well, it's a simple proportion problem. If I multiply this radius by 1 unit, this is a length, I would also multiply this arc. Sorry, if I multiply this by r units to go from 1 up to r, I would also multiply this arc by r units to go from theta up to r times theta units. Okay, so this gives us our next important formula for the lesson, which is the following. S is equal to r times theta, which is a lovely, simple, it's such a simple formula, and that's the power of radians. And in this formula, S is the arc length. Okay. Oops. What happened to my pen? There it is. Okay. So So S is the length of the arc. And keep in mind, theta, right here, must be in radians. Okay, so this is the power of using radians, is that it makes it very easy, very, very easy to calculate the length of an arc. And of course, the length of an arc, if you have an object moving in a circular motion, it's going to follow a circular arc. So the length of the arc is going to be a key component in describing the motion of something that's moving in a circular path. Okay, so we have our important formulas. We have the formula that given degrees will give us the number of radians. Given radians will give us the number of degrees. And finally, our formula right here, which given the radius and the angle will give us the arc length. Okay, so given those pieces of information, let's do a couple examples. And so example number 1. Let's actually pick a different color. Oops. Here we go. Let's go to sort of a, yeah, this color here. Okay, lovely color. All right, example number 1 is convert 120 degrees to radians. Okay, so pretty simple. We know the formula. And so we say 120 degrees times pi over 180 degrees. Okay, so that equals 120 degrees times pi. Oops. Okay, 120 pi over 180. And we can reduce this fraction. Divide top and bottom by, I guess that would be 40. And so I get 3 pi over 4. Okay, this is what we call an exact value. That is the exact value of the answer. If you wanted to, if you say 3 pi over 4, I don't really know what that is. You can always go to your calculator and say, okay, 3 pi divided by 4. And the decimal approximation is 2.36 if we round. Okay, so 3 pi over 4 approximately equal to 2.36 radians. So, sometimes I may ask for an exact value, which would be this right here, or if I ask for an approximate value, that will be, the decimal approximation, that would be this right here. So that's example number 1. And now let's do example number 2. So we wanted, for example number 2, let's do 73 degrees to radians. And same formula, right? We say, okay, 73 degrees times pi over 180 degrees. Okay, so 73 pi over 180. So when you have an angle like 73, this is, there are no common factors between 73 and 180. I don't believe there are. And so there's really no reducing you can do here. So typically for an angle like that, we'll just go ahead and give a decimal approximation. We'll plug this in the calculator, 73 pi divided by 180. And that gives us 1.27. So again, this is not an exact value. This is a decimal approximation. Okay, probably should have put radians, but no space for the first one. Anyway, okay. So that's the number of radians, and that right there is our answer. So now let's look at an example where we are given the number of radians and we turn that into degrees. All right, and let's switch the color up here. How about we'll go with a nice blue color. And all right, example. Oh, I didn't change my color. I thought I asked for blue. All right, let's see if that worked. There we go. Example number 3. Let's convert the angle 5 pi over 6 to degrees. 5 pi over 6 radians to degrees. Okay, and of course here we're going to take 5 pi over 6 times 180 over pi, because that's how we convert from radians to degrees. And let's see, pi, cancel out pi, and 180 divided by 6, I believe is 30, and 5 times 30 is equal to 150 degrees. So there we go, simple enough. And so that's our answer. 5 pi over 6 radians is equal to 150 degrees. And let's do one other quick example. Actually, we're going to do 2 other examples, but the last one's a little different. So this is going to be a straightforward one. Example number 4. We have 2.3 radians, and we want to convert that to degrees. And so we take 2.3 times 180 over pi. And we'll just plug that in the calculator. 2.3 times 180 divided by pi. And I get 131.78 degrees. So more of a decimal. This one comes out nice and even. And this one will be a decimal approximation. It's not an exact value. So 78.78 degrees. Okay. Now I want to do one more example, which has to do with the idea of arc length. So all these 4 examples, you notice I didn't use the arc length formula. I only used these formulas up here, right? Formulas for converting degrees to radians and radians to degrees. So now let's do one more example, and let's pick yet another color. How about, let's go back to green. Okay. And so last example of the video, example number 5. And let's say we have a 3-meter arm. Okay, 3-meter arm. Rotates by 25 degrees. And the question is, how far does the end move? So I like to draw diagrams, problem like this. So we have our arm, okay, and let's draw a sort of little, I don't know, wrenchy hand thing at the end of the arm, and oops, let's draw a straighter line here, okay, and so this right here is 25 degrees, and the question is, what is the length of that arc? Okay, that's the thing we want to find out. So first of all, if you recall, my formula for arc length was S equals R times theta. However, theta needs to be in radians. So before I can even solve this problem, I have to convert theta into radians. Okay, so we'll start with that. So theta is equal to 25 degrees times be pi over 180 degrees. And so I'll plug that in the calculator. 25 times pi divided by 180 degrees. All right, so I got that theta is equal to, approximately equal to 0.44. Okay, and so in order to figure out the arc length, we have, we need to actually know the radius too, right? Which is given in the problem. The radius is 3 meters. And so S is equal to 3 times 0.44. And so we go here and take that, multiply by 3, and we get 1.31. So 1.31. My unit is in meters, and that's it. That's the solution. So a 3-meter arm rotates by 25 degrees. The end of the arm will then move a total distance of 1.31 meters. So let's put that in the diagram. This is 1.31 meters, approximately rounded to the nearest millimeter. Okay, so that wraps up our video. Hopefully this was helpful in understanding what radians are and how to convert between radians and degrees. And I hope to see you in a future video.